Hello everyone, here we'll be discussing chapter 4.8, which is called Newton's method, and it discusses this method developed by Isaac Newton. And if you didn't know already, Isaac Newton essentially single-handedly discovered calculus. In fact, it's actually thought that Isaac Newton and Gottfried Leibniz each independently discovered calculus. Of course, Newton was from England, where Gottfried Leibniz was from Germany. So they didn't know or interact with each other, so they simultaneously supposedly discovered it. Though the notes of Newton are actually known, like they're in actual museums basically. And you can see his notes on kind of developing calculus on his own. And his notes date back further than Leibniz, but for whatever reason it's accredited to both of them. So recall Leibniz notation at dy over dx, so we see that their names come up here and there. But Newton's method is a method that it's pretty interesting. It involves derivative, of course, you can kind of see it in the formulation here. But it is this so-called recursion, which I'll explain what that means in a second, that describes a way of finding a root of a solution using calculus, which is a very, very, very useful application of calculus. And we will be applying it to a few different examples, but mostly it's to approximate things or to find solutions to an equation. That's basically it. So Newton's method says if r is a root or solution to f of x equals 0, so that means plugging in r into f of x will give you 0. So basically it's an x-intercept of the function, or of the graph of the function. Then the limit as n goes to infinity of x sub n is equal to r, where x sub n plus 1 is equal to xn minus f of xn over f prime of xn. So this is kind of like the main equation we'll be using. And this is called a recursion or recurrence, where x1 is just a guess. Now, again, I said this was called a recursion or recurrence, but in fact, what people say usually is that this describes the relationship of this sequence of x of n recursively. So there may not be an actual formula to get to the 100th one. You kind of have to jump through each intermediate one. So you find x1 and then plug x1 into this, it'll give you x2. Then plug x2 in, you'll get x3 and so on. Now I'm going to explain visually why this works. So it's not really a proof, it's kind of like a visualization, but I think it's pretty cool. So basically we have some curve. So I'm just going to make it, I'm not going to make it super wavy or anything. Let's just say it's a curve like this. And that's f of x. Now it may be curvy, but as it passes through, just imagine it's smooth and it doesn't squiggle or anything. Even if it did squiggle, this method will still work because you can zoom in enough to the x-axis where it passes through at that x value r, such that it's smooth either like this or the other way around, but it passes through. So even if it's squiggled like this, I made it look like that's the y-axis. I didn't mean to do that. But there we go. Even if it's squiggled through like this, if you keep zooming in, you'll just get that kind of shape here. So you can always, again, I drew the y-axis, sorry. But you can always do that. You can always zoom in so that you just get kind of like this smooth curve as it passes through the x-axis at a particular point, and that's what we care about. So the visualization is that we actually have to consider a value that's close to r, that we think is close to r, so it's our guess, and that's x1. So we're kind of, imagine we're pretty zoomed in here. So imagine this is x1, let's say over here. So what you do is you can actually project x1 to f, and you'll get, of course, f of x1. Okay, good. But then, if you create the tangent line at this point of tangency, it'll look something like this. And notice, this point cannot pass r, because if it did, then it wouldn't be tangent. Unless x1 is so far away from it that it passes through a curve or a loop, or not loop, but through a kind of bump or something like that. But if we're assuming x1 is close to r where that doesn't happen, then actually you get a point that's closer. So we can call this new point intersection x2. And then we play the same game essentially. And again, assuming there's no weird dips in between, this will always happen. Project to the function to get f of x2. Create a tangent line. And look at that. The tangent line will never pass r. It'll still be on the same side of r. but it gets closer and closer and closer to r. How crazy. So then you can repeat this process, call that x3, and keep going until you're satisfied with your approximation. And if you want to, you can kind of compare with the calculator, of course, depending on the actual function that we're dealing with. So we'll be doing a few examples where we can and others where we kind of can't. So I didn't actually describe what is happening with this recursion, but basically this is how you find x2, because x2 is the intersection between the tangent line and the x-axis. So recall from linearization that the line of tangency at x1 is given by f prime of x1 times x minus x1 plus f of x1. Okay, so I think that's pretty simple to see. That's just the equation for the tangent line at the point of tangency, where the x value is x1. But if we want this line to cross the x-axis, we're setting its y value equal to 0. Great. And the x value we get in solving this is what we call x2. So I'm going to replace this x with x sub 2. And then if you solve, well, notice all you really need to do is kind of distribute this. Or in fact, we don't even need to distribute. Just subtract this to the other side. So you get negative f of x1 equals f prime of x1 times x2 minus x1. And hopefully you kind of see where this is going. Just divide both sides by f prime of x1, like that. These cancel. And then we get x minus x2, or x2 minus x1 I should say, is equal to negative this quotient f prime, or f over f prime, excuse me. There we go, like that. So f of x1 over f prime of x1. And now what we need to do is really just add x1 to the other side, and we indeed get that x2 is equal to x1 minus f of x1 over f prime of x1. And you can kind of see that this is a very general statement. I mean, it doesn't really depend on what x1 is. In fact, if you relabel x2 as your new x1, then the next x value, x3, would be your new x2. So this works all the time. Meaning, if you replace the ones with n's, then this subscript 2 would be the next n, which would be n plus 1. So we indeed get this. So it's all based on this visualization of tangent lines. You get a point, guess it, project to the function, create a tangent line, you get closer to the actual x-intercept that we're trying to look for. Okay, so I think I've spoken enough here, and now let's move on and see some examples. Right, so this is a pretty kind of maybe boring example, but I think it's cool because the square root of 2 is actually really hard to find by hand. Of course, you can just punch it in your calculator and you'll get 1.414 something. Kind of spoiling it, but that's just what I remember off the top of my head. And the square root of 2 is one of those really unobvious values. And in fact, I always like asking people, what's the square root of 2? Because people that aren't really into math don't really know. So they may think, oh, it's 1 or it's 2 or something stupid like that. Which isn't really stupid because, if you don't think about it too much, of course you're not going to know. But the square root of 2 is just a really fantastic number. It's basically known as the first irrational number, known irrational number. So you can write it as a fraction of 2 integers, which is kind of interesting. There's actually a really sad story about this. Apparently, this Greek mathematician, who was a Pythagorean apparently, proved, actually using the Pythagorean theorem somehow, that if you have a right triangle whose sides are 1 and 1, then the hypotenuse is to the square root of 2, and he proved that you can't, so this was known, but he proved that you can write this as a fraction of integers. The proof is a little extensive, but it's not too bad. Basically, you assume it's a fraction, then you square both sides, manipulate it, and then you get a new fraction, but if you assume this fraction was already reduced, then it's a contradiction. Which sounds weird, but it's actually a legitimate proof, believe it or not. It contradicts that it was already, that the two parts of the fraction didn't have any common factor. But anyways, he proved that it was irrational and they drowned him because they took it that seriously. So irrational numbers are a really, really huge achievement in mathematics because up to that point, the Greeks basically thought, that all numbers were rational, that there were no such thing as irrational numbers, which is a pretty powerful thing to prove. Of course, it may have been known to other people, but the Greeks were that's really the most we have as far as written documentation of history of mathematics. Obviously, I'm rambling, so let's get on with this. So I want a function whose x-intercept is radical 2. So the way we do this is we just let it equal the square root of 2 like this, and then we can square both sides and solve for 0 so that we have a function of all we know radicals. Of course, you could just do this and call this your function, but then plugging things into this is hard and it's not really doable because you have radical 2 already. We're trying to find radical 2. So the square root of 2 we don't know, but the number 2 we do know. So instead what I'm going to do is square both sides to get x squared is equal to 2, and then I'm going to subtract 2 to get this, and this is going to be our function. So I'm just going to write f of x is equal to x squared minus 2. Perfect. So now what? Well, this is the function whose root is radical 2, but there's actually 2 roots here, because if you graph this, of course, you get a parabola shifted down 2 units. But we know this indeed actually has 2 solutions. One's the square root of 2, and one is negative the square root of 2. So this gives us a good guess. We can start on the right of this, so we can pick something like 2. Because 2 squared is 4, not 2, which is bigger than 2. So that means 2 is larger than the square root of 2. Awesome. So with that being said, we're going to have our first guess be 2, and we're just going to continue from this. But first, to get this recursion set up, well, let's see. We need to find f prime first. And notice f prime of x is equal to 2x. And setting this up now, we get xn plus 1 is equal to xn minus f of xn, which is xn squared minus 2, over f prime of xn, which is 2xn. Now, something I like to do at this point is to, let me just think for a second here, right, would be to multiply top and bottom of this by xn, so that we actually get a, or by 2xn, I guess, so we get a common denominator and it's a little easier on us. So I'm going to rewrite this xn as, if you don't mind, 2xn squared, because I'm multiplying top and bottom of that fraction by 2xn to get that common denominator. Perfect. So now we can write this as 2xn minus xn squared. So 2xn squared minus xn squared is 1xn squared. But then the negative distributes, so we get plus 2 all over 2xn, like that. And in fact, maybe you can actually split this up as xn. Yeah, that would be kind of funny. So if you split this up, you get xn squared over 2xn, the xn's cancel. So you get xn over 2, plus 2 over 2xn, the 2's cancel, so you get 1 over xn like this. But I think, either one of these are okay, but I think I'm going to use this one here. So now our guess again is going to be x1 is equal to 2. We're going to plug it in and see what x2 is. And in fact, let me erase some things here so we can just do that on the spot. So remember, this gives us x sub n plus 1. So if x1 is equal to 2, let me just write that here, then x2 is equal to plug 2 into this. So we get 2 squared is 4, plus 2 over 2 times 2, which is 6 over 4, which is 3 halves, which is 1.5. And that's actually closer because remember I said this is about 1.41. And then we can do it again. It's going to be a little harder, but let's see if we can do it. So when you plug in 3 over 2 into this, well, let's see. So we get 3 over 2 squared, which is 9 over 4. 9 over 4 is 2.25. I'll just write it as a fraction. I like fractions. So 9 over 4 plus 2, but notice 2 is 8 over 4, so that helps. Over 2 times 3 over 2, because this is 3 over 2. So here these cancel, so we get over 3. These actually combine to 9 plus 8 is 17 over 4. And this is actually the same as 17 over 12, which I'll have to use my calculator for this. And I got 1.41666666. And if you're brave enough, you can actually do this by hand. Now, I'm actually going to do this. I'm going to write all of these with about 7 decimal places because you want to be 6 decimal places of accuracy. So that way we can kind of see and try to track the decimals here. Now, it sounds kind of weird, but it's actually going to be quite cool. So if we round, this is a 7. So I'm going to round to 7 decimal places and we'll see where it stops. So now we're just going to see a list of values here. So I'm going to erase all this and write those values. All right, so there we go. Here's x3, x4, x5, and x6. And you can kind of see that after x5, it's actually the same. And if you were to do x7, it would be the same as well. And of course, remember that these x values are getting closer and closer to the actual x value we want. Now notice really here we're approximating, so these are all not actual equality, they're all approximate. So this is kind of good to know because it's a very important idea that we're not actually solving, we're approximating. I mean, I guess we're solving to some extent, but it's how accurate you want to be. Now, of course, the exact value of radical 2 is just radical 2. That's the way you write it. But the approximation of radical 2 is this. And in fact, if you were to use your calculator, you'd get exactly this. Only it's actually 3562, but the 5 rounds to 6. But this is indeed correct at 6 decimal places. Notice 1, 2, 3, 4, 5, 6. There we go. Right. So it's pretty useful to know Newton's method and notice that it's actually pretty quick. Now it's coincidence that at the sixth one we get 6 places of accuracy. Also, it depends on your guess. So notice if you guessed 1.4 or something like that, which actually is pretty simple to do because notice that 14 squared is 196, 15 squared is 225. So that means 1.4 squared would be 1.96 when you divide both sides by 10, or by 100, I guess. Because notice, since 100 is 10 squared, dividing 1.4, or dividing 14 squared by 100 is dividing 14 by 10 all squared, really. So basically you get this. And since this is close to 2 and less than 2, then 1.4 is actually less than radical 2. But that's an underestimate, not an overestimate, but it still works actually. The idea still works, in fact. So you can always try that, but again, just because you get something close doesn't mean you'll actually get a better answer, because it's possible that the tangent line may be curved enough so it throws you off further away and then come closer. In this case, it seems like we're getting closer and closer and closer, but some values may fluctuate. It just depends on your guess. You can try different values if you want to take a guess and run the process, and then you'll kind of see where you arrive at a point of accuracy that you're comfortable with. But again, we're going to move on beyond actually approximating a value to now finally solving an equation. All right, so here we want to find all solutions to this equation, this cubic polynomial equation, to 4 decimal places of accuracy. Now apparently, according to Newton's notes, this was the actual function he used to demonstrate his method. So it's going to be interesting for us to tamper with it, but what I want to do is I want to actually first show that there's only one solution. And I'm going to basically do that by graphing, and notice it's a cubic with a leading coefficient of 1. So the graph exaggeratively may look something like this. So it has to pass through the x-axis at least once. So imagine floating the x-axis like this. No matter where you put the x-axis, the graph passes through it at least once. At most 3 times, something like here. It could be 2 times if you pick maybe this point and this point, let's say. So drawing horizontal lines through a graph tells you at most or minimum how many solutions there are to that equation being equal to 0. But now, what I want to do though is I want to basically find these points, and I want to show that they're both, if they exist, they're both below or above the x-axis, and there's no way we can pass through them. To show there's only one solution. So I know that sounds weird, but we'll see that right now. And of course, to show that there's one solution, well, I kind of just did that. But you can use actually the intermediate value theorem. So we're going to pick some values. One will output a positive value, and one will output a negative value. So notice we're going to call this function f of x. So I think that part's kind of clear. So now notice when you plug in 0, clearly you get negative 5. So it's a negative value, so it's less than 0. Good. And now we want to plug in some value that will give us a positive. Now if you plug in 1, well, notice you get 1 minus 2, that's negative 1, minus 5 is going to be negative still. But if you plug in 2, well, I think it's going to be positive. Maybe not actually, because when you plug in 2, you get 8. Yeah, it's going to be 8 minus 4, which is 4 minus 5 is still negative actually. Ugh. What about 3 now? The fact that it's a cubic tells me if you plug in a number large enough, the cube is going to overcome the other lower powers, hopefully. And that appears to be the case actually, because when you plug in 3, you get 27 minus 6 minus 5, that's 27 minus 11, which is actually 16, and that's bigger than 0. So basically what we found out is that if 0 is over here, and positive 1, positive 2, and then 3, we've actually shown that 3 gives us a positive value, 2 gives us a negative value, 1 gives us a negative value, and 0 gives us a negative value. Now, I didn't actually write down what they were, I wrote down what they were, but I didn't actually list them out, so I can't go back to them. But at least we know it must pass through by intermediate value theorem, the x-axis somewhere in between 2 and 3. So this implies that our solution, let's call it C, I guess, is in the interval 2 to 3. It's somewhere in between 2 and 3. Because 2 gives us a negative value and 3 gives us a positive value. Good. So now what? How can we show that this is the only solution? Well, I'm going to take the derivative of this. So f prime, notice, is going to be, it's going to be 3x squared minus 2. Okay, so now if we set that equal to 0, what do we get? If we set this equal to 0, we get x is equal to, notice adding 2 to the other side and dividing by 3 gives you x squared is 2/3. But then when you square root, you get two values. You get plus or minus the square root of radical 2/3, which we can approximate if we like. In fact, let me do that right now to approximate this value. So I got about 0.816, so this is about, we got plus or minus 0.816. So just to kind of have a visualization of what's going on, there are max and mins when the derivative is 0, so we have a legitimate horizontal tangent line about here, somewhere here, so it's about 0.816, and somewhere over here. So let me point at them. So we have a maximum and minimum, and in fact we can tell which one's which by considering the, so I'm just going to draw them, draw like this. So let's call these, I guess I could just label them. So we're going to pick 1 and -1 as our test points around them. So this is negative 0.816 and this is positive 0.816. Just like that. That's negative, that's positive. Good. So now these are where the derivative is 0, and now we can pick numbers around them. If you pick a -1 and plug it into f prime, we get, let's say, -1 squared times 3 is positive 3 minus 2 is positive 1. So it's positive in this region. When you pick a number in between them, let's say 0, plugging that in gives you negative, and then plugging plugging in 1 into this gives you 3 minus 2, which is positive. Just like that. So that means f prime is positive here, negative here, and positive here. And what that tells me is that it goes up and down, so there's a max here. Down then up, so there's a minimum here. And we can actually find out what the value is when we plug it into the original. So if we plug in 0.816 and negative 0.816 into them, you can figure it out on your own, but I'll tell you right now they're going to be negative values. And it's not too hard to see that they're negative, because it's a number less than 1. So notice when you plug in 1 here, we did that earlier, we get 1 minus 2 minus 5, that's -6. When you plug in 0.8, which is less than 1, you'll also get something that's negative. Notice plugging in 0 is still negative. So this for sure is going to be negative. So it's going to be down here somewhere. I'm not going to say exactly where it is, but I know it's for sure a minimum, obviously. So let's just say it's somewhere down here, let's say. And then here we know this is a maximum, but again, if you plug in negative 0.816 yourself, you can see that the function will be negative as well, so it's also below the x-axis. So the function has to look something like this. And it kind of continues. We just know at 2 it's negative, and at 3 it's positive. And for sure, these are the only curves. These are the only dips in the function, because these are where we have the horizontal tangent line, and that's it. So in other words, it can't go anywhere else. It can't pass through the x-axis again. If it did, then there'd be another maximum here, and actually in that case it would fail to be cubic, because cubic has this kind of at most 2 turning points, and we have these 2 turning points actually. So we've shown that there's only one solution. Great. So now we are going to test a value, and I'm going to start with x1 to be 3. And at this point, I'm going to have to erase things and then write a recursion from Newton's method and then plug in our guess, and we're good to go. Right, so this is our function, of course. Now, we could have had x1 be 2 or 3 because those are the endpoints of the interval we know where the solution is in between, but I just picked 3. Of course, notice I'm kind of picking the one that's larger than because concavity is concave up, so we're going to get a quicker value. But you can try plugging in 2, maybe you'll get actually faster, who knows. But let's see. So our recursion, remember, involves f and its derivative. We found f prime earlier, so just to remind us, that's 3x squared minus 2. And now our recursion set up due to Newton's method is x sub n plus 1 is equal to x sub n minus the function over the derivative evaluated at x sub n. Just like that. But now notice the function is just this, so I'm going to replace that with xn instead of x's, that is, just like this. And then f prime of xn is the derivative with xn's instead of x's, just like that. Now remember, I like to write this as one fraction, so if you don't mind, I'm going to write this as x sub n over 1. And multiply top and bottom by this. If you distribute x sub n into that, let me scoot this over so we have space here. So if you distribute xn into this for the numerator, we actually get 3xn cubed minus 2xn, like that, all over the same denominator now. Just like this. Now the minus I want to distribute into the top so that this becomes positive. Distribute the negative in. So we end up with 3xn cubed minus 2xn minus xn cubed plus 2xn. Oh, that's nice. So these actually cancel out, which is pretty coincidence, but fantastic. And then plus 5. So this is probably one of the reasons why Newton used this to demonstrate his method, because it simplifies nicely to 2xn cubed plus 5. Notice 3xn cubed minus xn cubed is 2xn cubed over 3xn squared minus 2. And that's, I think, where I'm going to leave this. And now we're going to plug in values. So remember, our first value is x1 is equal to 3. But remember how we do this. I'm going to write 5 places, and then we're going to track each of them. So right now I'm just going to go into plug and chug mode. Alright, so that was fun, and we end up getting this as a beginner answer, and this is of course the 4 decimal places of accuracy, so this is accurate, but if we want to round it, it will be 4/6. So I'm just going to round it like this. And this is actually the only solution rounded to 4 decimal places of accuracy of this function. Awesome. So now we're going to do something a little more exciting. It's not a polynomial equation. By the way, if you have a polynomial equation, you'll basically do what I did, but it's going to be a little weird when you have more than one solution, because you use intermediate value theorem to find out what integer subinterval it's in. Like here we found it was between 2 and 3, and then we use that. So you will basically do that with your polynomial equation, but you get like a bunch of different ones for each supposed 0, and then play that game to get you until you get all 3 or 5 or however many there are of them, which can be a little tedious, but the best we can do is try to make it fun, like I kind of tried to do here. So now I'm going to do something a little more exciting than the polynomial function. This will be one that will involve trig. It's going to be pretty exciting, so let's take a look at that right now. Right, so here we actually have 2 examples. One involves trig, one involves ln. So now notice this is an equation, not a function equals 0, but we can always make it like that by moving things around. So we're going to let f of x equal cosine of x minus x, because notice when it's equal to 0, add x to the other side to get this. And the way I got this was just subtracting x to one side to solve for 0, and then call that non-zero side f of x. Great. Now if we actually graph these, which is pretty helpful to do, y equals x is this line like this diagonal line, and cosine of x looks something like this. So just by graphing, you can clearly tell they only pass through, well, they only intersect once, and it looks like it may be a clear, just miss here, but it actually is not close at all. I just kind of made it look close. But you can verify that on your own. Notice these dips here happen in multiples of a pi over 2. So this is going to be, actually not pi over 2, this is going to be a pi. No, I'm sorry. This is Yeah, so this is a pi, this would be a negative pi. Sorry about that. So when you plug a negative pi into cosine, you get negative 1. But negative pi into x gives you negative pi, which is less than negative 1. So there's no worries there. It's really here where the solution is. So this is what we're trying to find. And here, this is actually an x-intercept of cosine, which is at pi over 2. Notice cosine of pi over 2 is 0. So in fact, that's going to be, I think, our guess here. So I'm going to plug in x1 to be pi over 2. Of course, this is really calculative work. Unlike the previous ones where you can kind of do by hand, this one will be extreme calculative work. But now, of course, to set up the recursion, we're going to get xn plus 1 is equal to x of n minus the function cosine of xn minus xn. Let me put parentheses here just to denote that we're doing cosine of that and then minus this. So that's our function. And then over the derivative, derivative of cosine is a negative sine of xn minus derivative of x is 1. Now, I don't like that these are both negative, but we can pull out the negative like this from the denominator and bring the negative out on top to make this a plus, to get rid of it entirely. So we pull the negative out to make the fraction positive, which is nice that we can do that. Now, instead of actually writing this as a fraction, I'm going to leave it like this, just using my calculator. It's going to take a little bit of time, but it's not too bad. Now, from this, our guess will maybe be pi over 2. You can try other values to see, but I think, if you half it, it looks like this is a little more than halfway. Pi over 2 is 0.7, so if you want to, pi over 2 is 1.57. So if you want to try 1, maybe that's an okay spot to guess. But of course, your calculator needs to be in radians because these x values that we're taking cosine and sine of are not in degrees, but in radians, of course, they're just numbers, which we often think of as in radians. So I'm going to start with pi over 2. So x1 is going to be pi over 2, which I'll actually write out. So it's going to be 1.57. I didn't say how accurate, but I'll just do 4 places of accuracy. So I'm going to run it for the calculator and see what we get for these values. Right, so for this next one, there are a few ways of going about actually defining the function. I was just going to subtract this to that side and call that f of x, but as it turns out, the recursion you get is actually not the greatest. It's best really to multiply both sides by x minus 3, like this, and then subtract 1 to the other side. So that'll be equal to 0, so we're going to call this f of x. So the root of this equation will be a 0 or x-intercept of this function. Great. So that means to find its derivative, notice all we need to do really is use product rule here, which at first sounds a little annoying, but it's not too bad. Derivative of x minus 3 is 1 times ln of x, plus x minus 3 times derivative of ln of x, remember, is 1 over x. So we really get x minus 3 over x. And if you actually split this up, you get 1 over 3 minus x. 1 over 3 minus 3 over x is what I meant to say. Good. So now from this, we can get the recursion pretty simply. It's just xn plus 1 is equal to xn minus basically the function over its derivative, but with xn instead of x's. So that's xn minus 3 times ln of xn minus 1 over ln of xn, let me read parentheses here just to be safe, plus 1 minus 3 over xn. Now, if you want to clear denominators by multiplying top and bottom by xn, knock yourself out. I'm going to leave it like this, though. Now, as far as what I think a good guess will be, you can graph these. They're not too difficult to graph. ln of x, we've seen the graph of that a few times already. It looks something like this. It has an intercept here at 1 because ln of 1 is 0. And 1 over x actually looks like this kind of a shape, if you can imagine that. 1 over x minus 3 is just a shift of that to the right 3 units. So actually, if you do that, if you go over 3 units to the right, you end up getting this vertical asymptote here, and an image that looks something like this. Ooh, look at that. So what does that tell us? There's actually 2 solutions. Funny. So one solution is going to be less than 1, it looks like. It looks like it has to be because it's below the x-axis. So we'll plug in 1 here. So I'm going to plug in 1, and hopefully we get something less than 1 as our value. So we're going to plug in, let me just write it over here. x1 is equal to, well, 1. And then over here, we're going to plug in something a little bigger than 3. We can plug in 4. So we got x1 is equal to 1, and then alternatively, x1 is equal to 4. So let me clean this up and write that out right now. Right, so I've cleaned it up. We have x1 is equal to 1, and x1 is equal to, let's say, 4, and this is alternatively. So now we're going to run through the process by plugging these values in and seeing if we get values that make sense. Alright, so here are our solutions, and of course the 4 decimal places of accuracy, I'm just going to write them as x is approximately 0.6531 rounding to 4, and then 3.7557 again rounded to 4 decimal places. And notice these are about what we estimated. 1's less than 1, and 1 was a little bigger than 3. It's actually pretty bigger than 3, but that's fine. And that's actually going to be the end for this section here on 4.8, Newton's method. And again, it was pretty cool. We just found it basically an application of derivatives that allow us to solve equations finally, which is something that was kind of difficult to do from algebra, but now we can do this with calculus. The only catch is that it's approximating, so we don't get exact values. So if you think of like solutions of quadratics that involve radicals, like 2 plus radical 3 all over 4 or something like that, we won't get that exactly. We'll get an approximation of that, but there's no way for us to use this method to find an exact form of a solution, which is a little unfortunate, but that may be good enough, who knows. So I'll see you in the next video for 4.9. We'll be discussing the grand finale for chapter 4, where the course has a sudden shift. So I'm not going to spoil the surprise, but we'll get there, and you'll see when you see the title what it's really all about, because it's kind of self-explanatory. But anyways, I'll see you then. Thanks for watching. Hope you enjoyed, and I'll see you then.